Alright guys, so since we are asynchronous today, I wanted to take some time to talk about constantly accelerated motion and really try to connect what we talked about with graphs of motion with the equations of motion which I introduced to you at the end of last week. So let's start by considering a situation where you have an object that has a constant acceleration, and let's assume that that acceleration happens to be positive. Now, we haven't talked about acceleration versus time graphs yet, but I think you could figure out, you have enough knowledge at this point, that if we were going to graph acceleration versus time, and we're talking about something having constant acceleration, and it's positive, then the graph is going to be a horizontal line above the t-axis. So we're just going to have a horizontal line indicating we have constant acceleration. It's not changing its acceleration, and it happens to be some positive value. Okay, so that's pretty straightforward. Now, imagine what a v versus t, a velocity versus time graph would look like that indicates the same thing, that indicates constant positive acceleration. Okay? Let's assume for a second that it starts at some positive velocity and it has a positive constant acceleration. Right, if you think of the modern Galileo lab, it's a good example of this. The graph would be a linear graph, and since we said it starts with a positive velocity, I drew it above the t-axis and with a positive slope indicating that it is accelerating in the positive direction. Okay? Now, imagine what a position versus time graph would look like for this type of motion. So if an object starts out at a low velocity that's positive and gets faster and faster in the positive direction, we should expect that it would curve opening upwards like this. Okay? So I don't think that the shapes of these three graphs are all that surprising. However, let's think about this. This is a straight line. You guys know from algebra that a straight line has the equation y equals mx plus b. Okay, but think about how that general equation applies to this specific instance. In this specific instance, the y-intercept of the graph is the starting velocity. So this is the original velocity. The slope of this graph is the acceleration. And what we have on the x-axis is time. What we have on the y-axis is the velocity. Sometimes we'll put v final. But this should look familiar. This is one of those three equations that we introduced on Friday. All right? Any object that has constant acceleration is going to have a velocity versus time function that's linear. So that's where this comes from. We can rewrite it. Like I said, sometimes we'll use the subscript f. So we can say vf equals vo plus at, like so. Okay, now, this function is a curve. Some folks would say, oh, it's an exponential function. Turns out it's not exponential. It's actually a quadratic function. Okay, if you remember what a quadratic looks like, the general form of a quadratic, ax squared plus bx plus c equals 0. Okay. In this particular situation, all right, what we're plotting on the vertical axis is position. What we're plotting on the horizontal axis is time. So we can replace the x's with t's. All right. And it turns out that the specific equation that fits this scenario looks like this. I'm going to try to squeeze it in here. AT squared. All right, so that says x equals x naught plus v naught t plus 1/2 AT squared. This is a quadratic function, and if we subtract x naught from both sides, we could rewrite it in the form we saw it in class, which was delta x, the change in position, the displacement, equals VOT plus 1/2 AT squared. Now, for those of you that are in calculus, you could prove, for example, that the derivative of this function gives you this. All right, the derivative of this function gives you a constant function, or you could integrate and work backwards. So the integral of this gives you that, and the integral of this gives you that. Again, you don't need to know calculus to be able to do AP Physics 1, but having that knowledge isn't, certainly not going to detract from your understanding. Okay, so this equation here and this equation here both describe position or velocity of an object as a function of time when it has a constant acceleration. In fact, we could go back and model these equations to the modern Galileo lab and see why a quadratic fits in the position versus time for the bowling ball, or a linear function fits for the velocity versus time for the bowling ball. Now, you also saw a third equation in the notes, and that one looked like this. VF squared equals VO squared plus 2A delta x. I like to call this equation the no time equation, because if you look at it, out of the three, it's the one that doesn't have a t in it. Where this comes from is just algebraic manipulation. Okay, if we solve one of these two equations for t, and then we substitute it into the second equation and rearrange it, we end up with this relationship. So this is helpful when we have a situation where we need to know how fast an object is moving when it's at a certain spot, instead of how fast it's moving at a certain time or where it is at a certain time. This one takes time out of the picture and allows us to look at it from a different perspective. So I wanted to give you this heads up so you can understand a little bit better where the equations of motion came from and be able to connect them to the equations and being able to, or connect them to the graphs, I should say, and be able to put those two together and help reinforce your understanding.